Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. So the enthalpy or H of a system is the sum of the internal energy of the system and the product of pressure and volume. And so you can see the calculation or the equation associated with enthalpy, which is shown for you here. Well, oftentimes you can measure enthalpy, and what will end up happening is the reaction is the heat evolved in a reaction at constant pressure. Well, if you have constant pressure, what ends up happening is several of these variables are going to end up falling out of the equation. And so if you remember that energy is equal to heat plus work, and we're saying that we're now adding that to the product of pressure times volume. Well, if we substitute in what work is equivalent to, we could say that the work, the heat plus the work, which is negative pressure times the change in volume, plus pressure times volume. Well, if we were to do that substitution, what we end up seeing is that these portions cancel out. And what remains is that the enthalpy, or H, is equal to just the heat of the reaction at constant pressure. And so this is what we're going to be utilizing as we're solving these problems. Now, often the enthalpy or the delta H and the energy or the delta E are similar in value, but you can see large differences that exist whenever you're dealing with those reactions that produce large quantities of gases. So what this allows us to do is to actually qualify what types of reactions we're dealing with by measuring this enthalpy value. When the enthalpy is a negative value, that means that the heat is being released by the system. Remember, enthalpy is equal to just heat. So if you have negative values, that means that the heat is leaving the system. And we can then classify those types of reactions as exothermic reaction. Exo meaning the heat is exiting. If the enthalpy of a system is a positive value, well, then that means that the heat is being absorbed. It's coming into the system. And so we call that an endothermic reaction, like it's entering. So exothermic, it's leaving. Endothermic, it's entering. And so you're going to want to be able to use this vocabulary as you're thinking about the reactions that you're dealing with. So you've seen both of these concepts in action. If you've ever used one of those chemical heat packs, like if you go hiking or camping, you have this little pack that it starts off at room temperature. Well, then you crack it and shake it, and then all of a sudden there's this heat that's being released from this little packet. Well, what's happening there is that the iron fillings that are inside are being oxidized, and it's allowing the energy to be released from that overall reaction. The result, your hands end up getting warmer as that release of heat happens from the reaction. You've also likely experienced an endothermic reaction before if you've ever used a similar cold pack. So those cold packs contain ammonium nitrate. And so when you, again, crack and shake, it allows that ammonium nitrate to dissolve in water. And as that's taking place, it actually starts to absorb the heat from the surrounding areas. So as a result, the surroundings start getting colder as the ice pack is absorbing the heat from your body. So if we take a molecular view of what's happening in these exo or versus endothermic reactions, again, for an exothermic reaction, the surrounding temperature will rise due to this release in thermal energy by the reaction. And this extra thermal energy comes from the conversion of some of the chemical potential energy into kinetic energy. And during this process, we have new bonds that are being created and old bonds that are being broken. And the end result is that the reaction has less potential energy than the reactant. So the products have less compared to the reactants. Thus, you're in the deficit, which means you have let go of heat, which means it's an exothermic reaction. Now, if we compare that to an endothermic reaction, it's basically the opposite. The surroundings of the temperature drop due to absorbing heat through this reaction. Again, we're still breaking and making new bonds, but now in this case, the products will have more energy than the reactants, and that energy is then absorbed into the material itself. And so you now have more of this energy that's now converted into chemical potential energy that can be stored within the products. Now, the enthalpy change of a chemical reaction is considered to be an extensive property. We learned that word back in chapter 1. So extensive means it's dependent on how much is present. So the more you have of a reactant, the larger the enthalpy change will be, or the less you have a reactant, the less it will be. And we can use the mole amounts, those coefficients, to create a ratio between the molecule or the compound or the element itself and the enthalpy. So in this case, we could say if we look at the ratio of the propane C3H8 to the enthalpy, it's a 1 mole ratio to it. If we looked at oxygen, it would be 5 to the enthalpy value, carbon dioxide 3, hydrogen 4. So this becomes a ratio that we can use to convert and predict how much energy or heat might be associated with some of these reactions. And so you can see here, for if we had 1 mole of C3H8, for every 1 mole that's put in, you release negative 2,044 kilojoules. Or similarly, for every 5 moles of oxygen that's placed in, you're still going to release the negative 2044. So notice again, these become conversion factors that can be used later. All right, so let's try solving a problem. So it says, how much heat is evolved in the complete combustion of 13.2 kilograms of C3H8? And so on the previous slide, we saw that that enthalpy value, it was 1 mole of C3H8 is to negative 2044 kilojoules of heat. And so now it becomes a stoichiometry problem, the same type of conversion factor that we've dealt with before. Our first objective is to get from this gram or kilogram unit to moles. And then once we're in the mole unit, we can utilize the ratio that exists between the substance and the enthalpy value. So we would start by saying 13.2 kilograms of C3H8. And we know the first step is to go from kilograms to grams. So we would say 1 kilogram of C3H8 is to 1 mole of C3H8. We could then now, not 1 mole, is to 1 gram of C3H8. Now, and we know that's actually 10 to the third grams of C3H8, so 13.2 kilograms. And then we're going to first convert from kilograms to grams. And then we can go from grams of C3H8 to moles of C3H8 using the molar mass. So we would calculate that and say 12.01 times 3 plus 1.01 times 8. And that's going to give us 44.11 grams on the bottom is to 1 mole on top. And now is where we can now implement this ratio, that 1 mole of C3H8 is to negative 2044 kilojoules. And so now if we plug this in, we have 13.2 times 1,000 times negative 2044 divided by 44.11. And that gets us an answer of negative 6.12 times 10 to the 5th kilojoules. So this amount of heat is being released, or this is an exothermic reaction as this process occurs. Okay. And now we'll try another problem. It says, how much heat is evolved when 0.483 grams of diamond, which is just an allotrope of copper, or of carbon, excuse me, is burned? And so again, we have 0.483, we're going to say just grams of carbon. Our first objective is to get to moles like we've always done before. And so now we're going to use carbon's molar mass to get to moles. And then we can use this enthalpy of combustion, this heat of combustion that's provided for us, and say that, well, 1 mole of carbon translated into a conversion factor is equal to negative 395.4 kilojoules. And we plug that in, and we get 0.483 times 395.4 divided by 12.01. And that'll get us an answer of negative 15.9 kilojoules. And again, that should make sense because we are evolving, we're losing heat, and so we have this negative value. This also would be considered an exothermic process. Okay. I hope this information helped you understand enthalpy and how to do calculations associated with it. Make sure you guys like, comment, and subscribe, and let me know other content you want to see. Come back for later videos, and we'll be discussing more energy-related topics. Have a great day. See you guys soon.